In part 17 of my educational series titled Classical Chemical Assay for Small-Scale Miners, Prospectors, and Hobbyists, we covered some of the calculations regarding acid-base titrations, the requirements for an acid-base titration, and more. Chemical indicators and their use were also mentioned as endpoint indicators, but not discussed by any degree of complexity. In this presentation, the focus will be on what an indicator is, its relationship with pH values, and how to choose an indicator for an acid-base titration. I am Rob Boyko, Boyko Minerals Exploration, and welcome back. To understand the reactions of indicators, one must understand the equilibrium of water. As you will discover going forward, there is a relationship with the indicators that are used. As mentioned earlier in a previous presentation, Kw is the term used for the equilibrium of water, that is H2O. The solubility reaction is as shown in this reaction equation, where Kw is equal to the molarity of Ka multiplied by the molarity of Kb. Ka is the equilibrium for acids, and Kb is the equilibrium for bases. Therefore, water is actually considered to be an acid or can be a base. Pure distilled water is neutral. Its Kw is listed as 1.0 times 10 to the minus 14. The breakdown is as shown. Kw is equal to 1.0 times 10 to the minus 14, which is equal to the molarity of the hydrogen multiplied by the molarity of the hydroxide. Kw is 1.0 times 10 to the minus 14, which is equal to x multiplied by x algebraically, where x represents the hydrogen and the hydroxide. Therefore, Kw is equal to 1.0 times 10 to the minus 14, which is equal to x squared. And Ka, therefore, is equal to the square root of 1.0 times 10 to the minus 14, which equals the square root of x squared. Or simply put, Ka is equal to 1.0 times 10 to the minus 7, which equals x. Now, Kw is equal to 1.0 times 10 to the minus 7 Ka multiplied by 1.0 times 10 to the minus 7 Kb. The pH of Ka is equal to the minus log of 1.0 times 10 to the minus 7, which equals 7. Since the pH of Ka is equal to the minus log of 1.0 times 10 to the minus 7, then the pOH is equal to 14 minus 7, which equals 7, or a pH of 7 on the scale. Thus, the equilibrium of pure water has a pH of 7, which is the neutral point on the pH scale. This represents the endpoint, which is the equilibrium point of the solubility of species. It is also the neutral point of a titration, the point where an acid or a base is neutralized. It must be noted that the endpoint may not have an equal molar concentration of each species in a solution, as will be shown in an upcoming slide in this presentation. Indicators of special properties. Their ability of being able to change color at particular pH values in a solution are invaluable as endpoint indicators. Their equivalent points can be achieved at different pH levels. The reaction between sample species and a titrant will determine the equivalence point. Most chemical indicators are weak acids in a protonated form. Protonated simply means that an indicator molecule can form a coordinated bond with a proton. Simply put, their color will change when the indicator's molecule deprotonates, that is, changes back to its original basic form. The designation generally given to an indicator is capital H, capital I-N. As a weak acid, they will dissociate in a solution in accordance with their Ka values as shown. The equation can then be rearranged to show that there is also a pH value associated with the indicator. As shown, the pH of an indicator is equal to the pKa plus the log of the basic form of the indicator divided by the acidic form of the indicator. In essence, the pH of the solution and the pKa of the indicator together determines the molar ratio between the basic and the acidic molecules and atoms of the indicator in solution. It is this ratio of the two species having different colors that determines the overall color of the solution at endpoint. For example, using the Henderson-Hasselbalch equation and an acidic solution having a pH value of 2.3, placing a few drops of phenol red indicator into the solution, what would the color change be? Well, phenol red has a Ka value of 5.0 times 10 to the minus 8. The equation is as shown, where pH is equal to the pKa value of the indicator plus the log of In divided by HIN. Well, pKa is equal to the minus log of Ka. Well, In, as discussed earlier, is the basic form of the indicator, and HIN is the acidic form. Therefore, the equation changes to pH equals the minus log plus the log of In divided by HIN. Consulting the acid-base indicator chart, phenol red changes color from yellow to red between pH 6.6 and 8.0. From the previous slide, the pKa for the phenol red equals the minus log of the 5.0 times 10 to the minus 8 Ka, which equates to 7.3 pKa. The equation algebraically becomes pH 2.3 equals pKa, which is 7.3, plus the log of In divided by HIN. Now algebraically this becomes 2.3 minus the 7.3 equals 7.3 minus 7.3 plus the log of In divided by HIN. Now this reduces to minus 5.0, which equals the log of In divided by HIN. Well, minus 5.0 translates to 1.0 times 10 to the minus fifth. Therefore, minus 5.0 equals 1.0 times 10 to the minus fifth, was equal to the 1 mole of In divided by the 1 mole of HIN. Therefore, 1.0 times 10 to the minus fifth is equal to the log of 1 divided by 1, which is equals 0. Well, you really can't have 0, but we do have 1.0 times 10 to the minus fifth left over. Well, the 1.10 to the minus fifth is equal to 1 over 100,000, or stoichiometrically equals 1 to 100,000, or 100,000 over 1. Well, the ratio is thus 100,000 to 1. This relates to 100,000 yellow molecules to 1 red molecule in a solution having a pH value of 2.3. Let's continue. The color chart for phenol red shows the color change in solutions at different pH levels. Now that accompanying graph represents the color change of phenol red at different pH levels. This is true for most indicators. The noticeable color change happens when the ratio is between In and HIN, which is between 1 to 10 and 10 to 1. The equation translates to a pH range within 1 pH unit of an indicator's pKa value. Therefore, the equation becomes pH is equal to pKa plus the log of In divided by HIN, which is pH is equal to pKa plus the log of 1 divided by 10. pH, in this case, equals minus 1. Or pH is equal to pKa plus the log of In divided by HIN, which is pH, which equals pKa plus the log of 10 divided by 1. The pH is then equal to plus 1. Phenol red will have a noticeable intermediate color between pKa minus 1 and pKa plus 1. In theory, for any given indicator, the pKa, that is the equivalence point, is in the middle of the pH range of the indicator's color change. For methyl orange, which changes color between 3.2 and 4.4, the endpoint would be 3.8. There are times when an acid-base indicator chart does not show the Ka or pKa value of an indicator, only a pH range. Therefore, it can only be assumed that the neutral point of the indicator is in the middle of the two pH values listed. This is only an estimation for a rough determination of the equivalence point. It can be calculated as shown, where the pKa is equal to 1/2 multiplied by the first pH value plus the second pH value. Now for phenol red, as shown, 0.5 multiplied by the 6.8 plus the 8.0 equates to 7.4, which is in the middle between 6.8 and 8.0. Now, if the Ka value was known, then a more accurate value can be determined, as the pKa is equal to the minus log of the Ka value. The estimation of any acid can be done with the method and calculations used that is going to be presented in this and the next few slides. For this example, vinegar is used, which is simply acetic acid. A spot plate, as shown, is commonly used for this procedure. In each sample well, a small amount of acetic acid is added. The concept is to use different acid-base indicators to approximate the pH value of the acid in each well to determine the pH range and thus the concentration range of the acid. As shown, neutral red, having a color that changes between pH range of 6.8 and 8.0, the color remained red when a few drops was added to the first well, top left in the plate. This shows that the pH value of the acid is below pH 6.8. Chlorophenol red was added to the second well. Again, no color change. Chlorophenol red changes pH between 5.2 and 6.8. Still no color change from yellow to red, indicating that the pH value is below 5.2. Bromocresol green was added to the third well. The color changed to blue. Bromocresol green changes color from yellow to blue between pH 3.0 and 4.6. To further refine the estimated pH value, methyl orange was added. The color changed from red to yellow in the fourth well. Methyl orange changes color between pH 3.2 and 4.4, indicating that the pH of the sample must be between 3.2 and 4.4. To replicate the last test, methyl orange was added and the color did change. By a process of elimination, the estimated pH value is somewhere between 3.2 and 4.4. Next slide. The next step in the process is to obtain the required information, starting with the reaction equation. The acetic acid in solution forms hydrogen ions and acetate ions. As shown, the ratio between the hydrogen ions and the acetate ions is 1:1. From the Ka table, the acetic acid has a Ka value of 1.8 times 10 to the minus fifth. The pH range of the methyl orange, which is a weak acid, from the indicator chart, has a range of 3.2 to 4.4. The range of pH values must be converted to the equivalent molar range of the indicator. The equation for the conversion is simply the antilog of the pH, which is 10 to the minus pH value. As shown, the pH of 3.2 is 6.3 times 10 to the minus fourth, and the pH of 4.4 is 4.0 times 10 to the minus fifth. To determine the molar concentration of the acetic acid, an ice table is used. These tables show the initial concentration of the sample and how they would dissociate with another species in a solution. In this case, it is the methyl orange. However, the term X is the unknown. However, we do have enough information to be able to calculate the molarity of the acetic acid, which is represented by the term X. The ice table shows that there will be a certain amount of dissociation, but not all of the acetic acid will dissociate at equilibrium due to the forward and reverse reactions. Since the mole rate between the indicator, the hydrogen, and the acetate is 1 to 1 to 1, the information obtained from the ice table can be used. 1.8 times 10 to the minus fifth, therefore, equals 6.3 times 10 to the minus 4 squared, divided by x minus 6.3 times 10 to the minus fourth. The equation can then be rearranged, where x minus 6.3 times 10 to the minus 4 is equal to 3.98 times 10 to the minus 7, divided by the 1.8 times 10 to the minus fifth. This is further reduced to x minus 6.3 times 10 to the minus 4, which is equal to 2.21 times 10 to the minus second. To obtain x, 6.3 times 10 to the minus 4 is added to the x minus 6.3 times 10 to the minus 4. This cancels out the 6.3 times 10 to the minus 4 algebraically, leaving just x. However, to balance the equation, the 6.3 times 10 to the minus 4 has to be added to the 2.21 times 10 to the minus second, giving a value of 2.273 times 10 to the minus second for x. The same is done for the 4.0 times 10 to the minus 5 algebraically. The 4.0 times 10 to the minus 5 in the table is rounded off. The actual is 3.98 times 10 to the minus fifth. The end result gives us a value of 1.28 times 10 to the minus 4. Therefore, the molar concentration range of the acetic acid would be 1.28 times 10 to the minus 4 to 2.27 times 10 to the minus second, where 1.28 times 10 to the minus 4 plus the 2.27 times 10 to the minus second multiplied by the 0.05 equals 1.1 times 10 to the minus second. This equates to a mean concentration of acetic acid as being 1.1 times 10 to the minus second molar, which is the same as an estimated concentration of 0.01 normal acetic acid. It should be quite obvious now that one can track the pH of a titration, as indicators are used as a tool for detecting the equivalence point. If using a base as the titrant, a few drops of an indicator that is added to an acid, the acid must have a pH value that is low enough to keep the indicator in its acidic state. To represent the indicator in its acidic state, the term HIN is used. Adding a base to the acid, it increases the pH of the solution. When the pH reaches equilibrium, the indicator loses its acidic property, becoming basic and changes color. The color change indicates the endpoint of the titration. This is the point where the slow addition of the base solution is stopped. The term endpoint and equivalence point are quite often interchanged and understood as being the same point. However, they are not actually the same point, and this too must be understood. The equivalence point is a single point stoichiometrically, where the base solution neutralizes the acid solution. It is the equilibrium point where the forward and reverse reactions take place. One additional molecule added shifts the reaction further to the right, neutralizing the indicator, which in turn changes color. The endpoint is defined by the indicator that is chosen. It depends on the speed of which the color change occurs. It could be fast or it could be slow. Hence, the titrant is added slowly to compensate for the slower reaction. By adding the titrant too quickly, the possibility of overshooting the equivalence point and the test or result will be an error. Therefore, the color change is the signal indicating the equivalence point. The volume of the titrant used to reach the endpoint is used to calculate the concentration of the sample. It is best to choose an indicator whose pKa value is as close to the pH value of the sample solution as was estimated by the aforementioned test with the spot plate. It is also best to add the titrant slowly to inhibit any error in overshooting the equivalence point by adding an excess amount of titrant. So what is the best pKa value when titrating a strong acid using a strong base? Consider a strong acid as having a pH value of 1 and a strong base having a pH value of 13. Equilibrium would occur at pH 7, approximately. It was shown that an intermediate color is noticeable between pKa -1 and pKa +1. Therefore, the first observable color change when the ratio between IN and HIN is approximately 1 to 10, as shown for the base. For the base that is titrated by an acid, the observable color change occurs when the ratio between IN and HIN is 10 to 1. As shown and illustrated, it requires two different indicators for each of these titrations. In practice, the first color change will not necessarily happen right at equivalence. The indicator, however, must be able to change color when the equivalent point is reached. A good indicator of choice begins to change color after the volume of titrant reaches the equivalence point. For a strong acid being titrated with a strong base, assuming 50 mils of a 0.1 molar hydrochloric acid, being titrated with a 0.1 molar sodium hydroxide, there will be a very sharp equivalence point. What this refers to is that there will be a very large change in pH when a small amount of sodium hydroxide is added to the hydrochloric acid. Sometimes it's just a single drop of the base solution. Any pH in this range will be reached after the addition of the same number of drops of the titrant. Now what this means is that any indicator will start to change color within its pH range, and therefore will signal equally when the equivalence has been reached. Now if the indicator changes color between 8.0 and 9.6, but the equivalent point is 6.8, the equivalent point would be overshot, resulting in an error. It also means that in a strong acid, strong base titration, a single drop of titrant could overshoot the equivalence point, resulting in a very sharp endpoint. Now consider an acetic acid being titrated with a sodium hydroxide titrant, a strong base. The equivalence point will not be that steep. The change in pH will not be that quick. Because of the smaller range of the pHs that will be passed, the indicator of choice must start to change color close to the solution's equivalent point compared to the strong acid-base titration. The endpoint for the weak acid strong base is much wider. Thus, these two graphs illustrate this concept. Both indicators, methyl red and thymol blue, is used. Now thymol blue turns red to yellow between pH 1.2 and 2.8, then to blue between pH 8.0 and 9.6. Methyl red changes to yellow between 4.8 and 6.0. Notice how both indicators will be yellow at pH 8.0. For the strong acid, methyl red starts to change color at roughly 50 milliliters of added base, whereas it starts to change color at about 15 milliliters if used to titrate a weak acid solution. This is far from the acetic acid's equivalent point. This illustrates the importance of choosing the correct indicator to use. To put it into perspective, the faster the indicator changes color within its pH range, the sharper the endpoint will be. The limitation is in choosing the right indicator. The approximate pH value of the sample solution must be known. Therefore, using the spot plate test would be the best method for approximating the sample solution's pH. The relative strengths of the Bronsted-Lowry acid and bases in aqueous solutions table shows the hydronium molecule, H3O, as an acid having a Ka value of 1.0. Hydronium dissociates into hydrogen atoms and water molecules. Water is a weak acid that has a Ka value of 1.0 times 10 to the minus 14, as listed in the table. What should be noted is that the larger the Ka value, the stronger the acid is, and the smaller the Ka value, the stronger the base is. Hydroxide, which has a formula of OH, and ammonia, NH3, are very weak acids, but extremely strong bases in solution. Hydronium is always present in water as part of the liquid, albeit a little in concentration. It is actually a water molecule with an extra hydrogen atom, sometimes referred to as heavy water. Water dissociates into hydrogen atoms and hydroxide polyatomic ions. Kw just represents the equilibrium constant for water. Since the hydrogen is the acidic part, or Ka, the hydroxide is the base part, or Kb. Hydrochloric acid is a strong acid, and sodium hydroxide a strong base. In solution, they will fully dissociate as shown in the reaction equation, completely neutralizing each other. The product, being a sodium salt, is neither acidic or basic. It has no effect on the pH of the solution, and therefore is also neutral. The result is that the pH value of the solution would be equal to or near 7. Therefore, all that is left is a salt in a weak acid solution, being the water. Since water, in essence, does slowly dissociate by a method of evaporation and having a Kw value of 1.0 times 10 to the minus 14, algebraically, Ka equals 1.0 times 10 to the minus 7, and Kb has the same value. pH is equal to the minus log of 1.0 times 10 to the minus 7, which is 7, which is the neutral point on the pH scale of 0 to 14. Since the solution would have a pH value approximately 7, the choice of indicator would naturally be Bromthal blue, having a pH range between 6.0 and 7.6. Now let's examine a titration of a strong acid and a weak base, where hydrochloric acid is titrated with a solution of 0.1 molar ammonium hydroxide. Adding ammonia, NH3, to water, the product becomes ammonium hydroxide in solution, NH4OH. The Kb for ammonia is 1.8 times 10 to the minus 5th. The Kb value represents the extent that the ammonium hydroxide dissociates into the ammonia ion and the hydroxide ion in water. Therefore, Kb equals the molar amount of ammonia multiplied by the molar amount of hydroxide, then divided by the molar amount of ammonia as shown. Ammonium hydroxide added to the hydrochloric acid all will dissociate into chlorine ions, ammonium ions, and water molecules. There is a buffer reaction that occurs. Now, a buffer reaction is one that resists changes in pH when small amounts of weak base is added to a strong acid, and vice versa. The ammonium in water reduces to ammonia and hydronium in water as shown. The ammonia becomes a strong base and the ammonium transforms into a weak conjugate acid. Therefore, the equivalence constant, Keq, is equal to the molar amount of the ammonia multiplied by the molar amount of the hydronium divided by the molar amount of ammonium. This formula can then be rearranged from the Kb equation above, where the molar amount of ammonia is equal to the molar amount of the hydroxide multiplied by the molar amount of the ammonium divided by Kb. Therefore, the equilibrium constant KEQ would be equal to the molar amount of the hydroxide multiplied by the molar amount of the hydronium and then multiplied by the molar amount of the ammonium, which is then divided by the molar amount of the ammonium multiplied by Kb. Mathematically, the ammonium can be cancelled out, and the equation is rewritten as KEW is equal to the molar amount of the hydroxide multiplied by the molar amount of the hydronium divided by Kb. This is equal to Kw divided by Kb. Now note that the reaction between the hydronium and the hydroxide creates water, hence the Kw in the equation. Also, the reaction between the ammonia and the hydronium creates water and ammonium, which is soluble, and thus the equation is also reduced to Kw divided by Kb. In addition to, note that the molarity of the ammonia equals the molarity of the hydronium at equivalence, and are the products formed from the ammonium during dissociation. Therefore, the molarity of the hydronium is equal to the square root of Kw divided by Kb, then multiplied by the molarity of the ammonium. For the hydrochloric acid being titrated by a 0,1 molar ammonium hydroxide, the molarity of the hydronium would be equal to the molarity of the hydrochloric acid, which is equal to the square root of the 1.0 times 10 to the minus 14 divided by the 1.8 times 10 to the minus 5th, and then multiplied by the 0.1 molar ammonium hydroxide, which equates to 7.45 times 10 to the minus 6 moles of H3O. Well, the pH is equal to the minus log of 7.45 times 10 to the minus 6, which equates to the pH value of 5.1. Therefore, the indicator that is chosen would be methyl red, having a pH between 4.8 and 6.0. Let's examine a practical situation. For example, someone diluted 20 milliliters of 0.5 normal ammonium hydroxide and labeled it as 0.09 normal, knowing that the molar ratios of the hydrochloric acid and the ammonium hydroxide is 1 to 1, and also knowing that after dissociation of the ions in water, they too will have ratios of 1 to 1, and that includes the hydronium in solution. The ammonium hydroxide can be normalized using a standard hydrochloric acid as a titrant. First, the molarity of the ammonium hydroxide needs to be known. Since 0.5 normal ammonium hydroxide was diluted to 100 milliliters, the dilution calculation shown gives us a value of 0.1 molar, which is equal to 0.01 normal ammonium hydroxide. The molarity of the hydronium, therefore, as calculated, is 7.45 times 10 to the minus 6, and the pH is equal to 5.1. The methyl red was chosen to be the indicator, and a few drops is added to the ammonium hydroxide. At the end point of the titration, where 20 milliliters of hydrochloric acid was added to cause the ammonium hydroxide to turn yellow, the total volume of the solution increases. Therefore, the molarity of the ammonium hydroxide decreases. The total volume is now 120 milliliters, and the molarity decreases to 0.083 molar. The pH value is now 5.2. This confirms that the methyl orange was the correct choice for this titration. Now let's examine the titration of a weak acid, such as acetic acid, and a strong base such as sodium hydroxide. CH3COOH is acetic acid, which will dissociate in water to become CH3COO, which is acetate. The Ka value for acetic acid is 1.8 times 10 to the minus 5th. The dissociation reaction with sodium hydroxide is shown, where the acetic acid dissociates to produce acetate, sodium ions, and water. There is also a buffer reaction that takes place. The acetate in solution reforms into acetic acid and hydroxide ions, as shown in the equation. The equilibrium constant is equal to the molar concentration of the acetic acid, multiplied by the molarity of the hydroxide ions, divided by the acetate. The equation can then be rearranged from the Ka equation for acetic acid to show the molarity of the acetic acid, which is equal to the molarity of the acetate, multiplied by the molarity of the hydrogen ions, divided by the Ka value. Keq then equals the molarity of the acetate, multiplied by the molarity of the hydrogen ions, then multiplied by the hydroxide ions, further divided by the molarity of the acetate multiplied by the Ka value of the acetic acid. Mathematically, the acetate can be cancelled out, and the equation is shortened. Keq is now shown to equal the molarity of the hydrogen ions, multiplied by the hydroxide ions, divided by Ka. Since hydrogen and hydroxide forms a water molecule, Keq is now equal to Kw divided by Ka. The molarity of the hydroxide is equal to the molarity of the acetic acid, as both are formed from the buffer equilibrium reaction. Therefore, the molarity of the hydroxide can be used to determine the pH value of the solution. The molarity of the hydroxide is equal to the square root of Kw divided by Ka, multiplied by the molar concentration of the acetate in solution. With a 0.1 molar sodium hydroxide, the molarity of the hydroxide is therefore the square root of 1.0 times 10 to the minus 14, divided by 1.8 times 10 to the minus 5th, multiplied by the 0.1 molar acetate, which equates to 7.45 times 10 to the minus 6. Note that the 0.1 molar of acetate is equal to the 0.1 molar sodium hydroxide. As the titrating solution is a strong base, the pOH is equal to the minus log of 7.45 times 10 to the minus 6, which equals 5.13. The pH value, therefore, is equal to 14 minus 5.13, which equates to a pH value of 8.87 on the pH scale. Phenolphthalein, which has a pH range of 8.0 to 10, would be the choice of indicator to use for this titration. To put it into perspective, taking 20 milliliters of 0.5 normal acetic acid and diluting to 100 milliliters and using sodium hydroxide as the titrant, the endpoint indicator used can confirm the results from the spot test. The important thing to realize is that a strong base is being used as the titrant. 20 milliliters of the base was added to the acetic acid to the endpoint. Therefore, the starting volume was 100 milliliters. With the 20 milliliters added, the total volume was 120 milliliters. The Ka value of the acetic acid from the Ka table is 1.0 times 10 to the minus 5th. The molar concentration of the dissociated product, being the acetate, is equal to the 0.5 normal sodium hydroxide multiplied by the initial 20 milliliters divided by the 120 milliliters, which is 0.083 molar acetate in solution. Note, the dissociation equation shows that the ratio between the acetate and the acetic acid is 1:1. The ratio between the acetic acid and the hydroxide is also 1:1. Therefore, the hydroxide can be used to calculate the molarity of the solution, where the molar amount is equal to the Kw divided by the Ka value of the acetic acid multiplied by the molar amount of the acetate. This equates to 6.8 times 10 to the minus 6 molar. The pOH is then equal to the minus log of 6.8 times 10 to the minus 6, which is 5.17. As the titrant is a strong base solution, the pH value is what is required. Therefore, 14 minus the 5.17 gives us a pH value of 8.8. Phenolphthalein has a range, a pH range that is, of 8.0 to 10.0. This was the indicator of choice, thus confirmed to be the correct choice of the indicator to be used. Now that we have discussed the basic knowledge around the acid-base indicators, how to choose the right indicator, and verify the indicator of choice, I can now talk about the how-to of determining the concentration of an unknown acid or standardize an acid using a primary standard solution. Using hydrofluoric acid as the unknown acid and sodium hydroxide as the base titrant, the dissociation reaction equation is as shown. The Ka value for the hydrofluoric acid is 6.6 times 10 to the minus 6. The water in the equation above dissociates into hydrogen and hydroxide. All will have a ratio of 1 to 1. Using a spot plate, a few drops of sample added to the wells of the spot plate, and using a drop or two, or slightly more, by process of elimination, the indicator of choice can be estimated. Using a 150 milliliter burette, add some standard sodium hydroxide solution and fill past the fill mark. Let it stand for a few minutes, then drain into a clean small beaker until the meniscus reaches the fill or zero mark. Set aside the beaker and discard safely later. Place 50 milliliters of the sample hydrofluoric acid into a second 200 milliliter beaker and titrate with the indicator chosen from the spot test to the endpoint. Do the calculations previously shown to confirm the indicator of choice as being the right choice. Repeat step 3 and add 50 milliliters of the hydrofluoric acid to a third clean beaker, etc. Add a few drops of indicator and titrate to the endpoint. Record the volume of titrate used. Repeat the procedure in step 6 3 times and calculate the average volume of sodium hydroxide used to titrate to the endpoint and record. This information is used to calculate the concentration of the hydrofluoric acid in solution. To find the molar concentration of the hydrofluoric acid in the solution, the number of moles of sodium hydroxide must be known. This is equal to the molar concentration of the sodium hydroxide, which is 0.2 molar, multiplied by the liters of solution, which is taken from the information recorded as shown in the table. Since 1 mole of hydrofluoric acid is equal to 1 mole of hydroxide, this equals 16 millimoles of sodium hydroxide in solution. The molarity of the hydrofluoric acid is equal to the number of moles of hydrofluoric acid divided by the number of liters of solution. Since 1 mole of hydroxide is equal to 1 mole of hydrofluoric acid, 16 millimoles divided by the 50 milliliters of the initial sample, the molarity of the hydrofluoric acid is therefore 0.032 molar, or 0.32 normal hydrofluoric acid. This process and procedure is used for most, if not all, acid-base titrations, as well as normalizing other compounds in solution. Now this concludes part 18 of this series. Endpoint indicators were discussed in relation to acid-base indicators, how to determine an indicator of choice, and how to confirm the indicator of choice, ending with the process of calculating the concentration of an unknown acid or base. I tried and hopefully succeeded in presenting the information in a way that anyone without a chemistry background would understand. I also hope that this presentation entices you to view, when published, Part 19 of this series on classical chemical analysis for small-scale miners, prospectors, and hobbyists. If you found this presentation interesting or know of someone who would benefit from this presentation or a series of presentations, please give it a like and a share. It's my only reward. To close, I included in the slide a short reel that was published by Chem Tech Talk. I hope that you find it interesting. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.